Hey physicists, this is a simple series circuit. We're going to run through the math on how to figure out V, I, and R, or the current, the voltage, and the resistance for each of those. So I'm going to give you some values here to begin with. We're going to say that this R1 is going to be equal to 10 ohms. We'll say that R2 is equal to 20 ohms, and we'll say that R3 is equal to 30 ohms. So that automatically fills these in down here, 10 ohms, 20 ohms, and 30 ohms. And those will be given to you in the problem. The other thing that may or may not be given to you in the problem is we're going to say the voltage of this battery is going to be a 12-volt battery. That ends up being our total voltage for the circuit that we're looking at, so I can fill this in as 12 volts there. Now, whenever I look at this, one of the things that we want to talk about is we're going to do what is called collapsing the circuit. And when we collapse the circuit, what we want to find is we want to find the equivalent resistance. And what that is it's the resistance that if I were to replace all of these resistors in the circuit with one resistor, what would the value of that one resistor be? So if I replace all the resistors in the circuit with one resistor, what would the value of that resistor be? The value of that resistor being. So collapsing the circuit, we'll collapse it down into one resistor and replace it as like the equivalent resistance. If I replace all of those resistors with one resistor, what would that value be? So for instance, since these are all in series, I can easily collapse them down into one resistor, or one light bulb in this case, and have a circuit that looks like that. So I would have a total voltage then that is 12 volts, and I want to know what that total resistance is if I collapse that. So think through, in a series circuit, how do we connect or combine our resistors? Remember that in a series circuit, those resistors add up and they literally just add. So when we put resistors in a series circuit, we get a bigger resistance. So if I want to find my total resistance here, I'm just going to have 10 plus 20 plus 30, and that's going to give me a total resistance of 60 ohms. 60 ohms. Now, the beauty in this is, now that we've found the total resistance and we have the total voltage, then can't we find what the total current is flowing through this circuit by doing across the row here Ohm's law, where we would have V equals IR. So I can take 12 volts equals I times my 60 ohms and calculate that to have a total current of 0.2 amps. So I can put in here 0.2 amps. Now, from here, what we can do then is, can't we find the individual current and the individual resistance or individual voltage on each of those resistors? So I can now find an I1 and a V1, an I2 and a V2, and an I3 and a V3. And think through what we know about series and parallel circuits. In a series circuit, what is constant? The current or the voltage? And we know that the answer to that is that the series current is constant, parallel voltage is constant. So in a series circuit, the current is what's constant, which means all of these currents are going to be 0.2 amps. So I know that this is going to be 0.2, I know that this is going to be 0.2, and I know that this is going to be 0.2. Now, don't we have two columns here, and we can find the third column, which is the voltage, by simply doing Ohm's law, V equals IR. So if I take and multiply 10 times 0.2, I get 2 volts. If I take and multiply 20 times 0.2, I get 4 volts. And if I take and multiply 30 times 0.2, I get 6 volts. And so there are my answers for my voltages: 2 volts, 4 volts, and 6 volts. And think through what we know about series circuits and the voltages. don't all of the voltages in a series circuit add up to be your total voltage? So 6 plus 4 plus 2 gives us 12, and that helps to confirm that we did that correctly. So that is a basic series circuit and calculating what the current and the voltage and the amperage is on each one of those things. Here we are with a simple parallel circuit. So we'll run through similar to what we just did with the series circuit. And we're going to keep the same to make life easy. We'll keep the same values for our resistors. So we'll leave this resistor 1 as 10 ohms. We'll leave resistor 2 as 20 ohms. And we'll leave resistor 3 as 30 ohms. So this would be 10, and this will be 20, and this will be 30 for those values. And then we'll also leave our voltage the same, and that was a 12-volt battery, which is similar to a car battery. So this would be 12 volts. Now, if I collapse this parallel circuit down into one resistor that replaces all of those resistors, because they're all in parallel, then literally I'm taking my battery is the only thing that's going to be there, and I'm going to have one light bulb that is in there instead of those 3 light bulbs. And I want to find out, what is that total R value in a parallel circuit? Now, remember, in a series circuit, we literally just add them up, because the concept is that when we put resistors in series, we get a bigger resistance than any of the individual resistors. Well, that relationship is an inverse relationship when we deal with a parallel circuit, so that as we add more resistors in a parallel circuit, we get a smaller resistance, and that resistance has to be smaller than the smallest resistor. So we know in this case, once we add those up, we're going to get a resistance that is less than 10. Now, the equation for that then is going to be 1 over RT, because that's our inverse relationship, is going to be 1 over 10 plus 1 over 20 plus 1 over 30. And in this case, what you want to do is find on your calculator the button is x to the negative 1, or maybe the button that is 1 over x, or if you know how to use the fraction button on your calculator, you would do that also. So I would do 10, hit the button, x to the negative 1, plus 20, hit the button, x to the negative 1, plus 30, hit the button, x to the negative 1. And whenever you do that, you end up with a value that is 0.183. Now, the most common mistake that I see from my students here is that they put 0.183 in as the answer for the total resistance. However, remember that that 0.183 is really equal to 1 over RT, so we have to flip it one more time. So we're going to hit that button one more time, x to the negative 1, and we get a value of 5.45. 5.45 ohms. And does that look reasonable based on what we said earlier? Yes, it is smaller than the smallest resistor, and our resistance went down to get us our total value of the resistance. Now things become quite a bit easier, because across the row, can't we use Ohm's law, where we do V equals IR, in order to solve for what the total current is flowing through that circuit? So we have our I total here, and we have our 12 for our volts. We have our I is what we're looking for, and we know that the resistance is that 5.45. So whenever we divide those, we end up with a current that is 2.2 amps. So 2.2 amps there. Now that we know the total current, the 2.2 amps, then can't we come back up to this original resistor and unpack or uncollapse those resistors? So now we can find an I1 and a V1, an I2 and a V2, and an I3 and a V3. And in a parallel circuit, what do we know about the current or the voltage? Which one of those is constant? So if you remember, we know SCC, PVC, series current constant, parallel voltage constant, which means that all of those voltages for the parallel circuit are going to be 12 volts, because they're all equal. So this is going to be 12, this is going to be 12, this is going to be 12. And what will happen with our currents then is our currents will divide up into the individual branches, or split, so that the total of all of the branches is the total current. So now we can take and do 12 divided by 10, which will give us our I total. And if I take 12 divided by 10, I'm going to get 1.2 amps. If I take 12 divided by 20, I'm going to get 0.6 amps. And if I take 12 divided by 30, I'm going to get 0.4 amps. And remember, like we just said, that our currents break up into the individual branches, or we can say that if I add all of these up, I can double check to see if I did it correctly, because it should equal my total. And 1.2 plus 0.6 plus 0.4 does give us 2.2 amps. And that would be a simple parallel circuit. Okay, now we move into some more interesting ones, physicists. We're going to move from simple circuits into complex circuits. Now, what makes this circuit complex? If you look at the circuit, there's not just a basic set of series light bulbs or series resistors, and not just a basic set of parallel. We have a combination of them where if you look at these top two, R2 and 3 are really in parallel with each other, because as soon as the electrons get to this point here, this is what we would call a junction point, where they have the option to go either that way or that way, depending on what the resistance values are. And that's what makes that a parallel circuit. But then those two together, aren't they in series with R1? Because in order to get to R2 and 3, the electrons have to go through R1, and that's what makes that a series circuit. So what we're going to do is we're going to follow the same numbers that we had earlier. We're going to make this still be 10 ohms. We'll make this still be 20 ohms. And we'll make this still be 30 ohms. And we'll make our battery still have a voltage of 12 volts, just because these numbers work really nicely and easily. So if I fill in my table, then I know that this is going to be 12 volts. I know that this is going to be 10 ohms. This is going to be 20 ohms. And this is going to be 30 ohms. So when I do this, what I'm going to do is I'm going to collapse these one step at a time, where I'm going to break down the either individual series or the individual parallels one step at a time. Now, the students oftentimes want to skip this step, which they can do mentally all the way up until we get our total resistance. But at the end, you'll see that once we start unpacking or uncollapsing those resistors, that these pictures become really, really essential. So what I'm going to do is I'm going to start with these two parallel ones at the top, like we said earlier. So I'm going to combine those two, and I'm going to get an R23 resistor. And isn't that resistor in series then with this R1 resistor? So R1 is still going to be 10. Kind of drew that over. How about I move that down here and say there's my resistor or my light bulb again. I'm going to say R1 is still going to be 10 ohms. Okay, now to find R23, because these were in parallel, remember that's going to be that inverse relationship. So what I'm going to end up doing then is taking 1 over R23. Actually, I'm going to draw that down here. 1 over R23 is going to give me 1 over 20 plus 1 over 30. And in order to solve for R23, remember I'm going to do 20, hit the inverse button, plus 30, hit the inverse button, and then I'm going to inverse it one final time. And that is going to give me a resistance for R23 of 12 ohms. So that's if I were to combine 2 and 3 together, I'm going to get a total of 12 ohms resistance for the two of those. So from there then, if I have that total resistance for R23, now can't I collapse these two as a simple series circuit and put them together as one resistor that is going to have a resistance, or light bulb, this is the symbol that I'm drawing here, that's going to be R123, or my total resistance. Now, in a series circuit, it's a whole lot easier. Remember, it's just the sum of the resistors. So I'm going to have 10 plus that 12.0, which is going to give me a total resistance of 22 ohms. So I'm going to have a total resistance of 22 ohms here. Now we get to something that is familiar. Don't I have across the row here? I have a total voltage, my total voltage being 12 volts. I have a total resistance of 22 ohms. So can't I find a total current by doing Ohm's law? V equals IR. I'm going to have 12 equals I times my resistance of 22. And that will give me a total current of 0.545454 all the way out for a while. So that gives me a total 0.5454. That's my amps. And what I have to do now, I can't just literally go down the row, because these aren't all series, these aren't all parallel. Now I want to work my way back and unpack, or uncollapse my resistors. And that's kind of what I was talking about earlier, is most students can get to this place mentally without drawing the pictures, but as we start unpacking or uncollapsing, the pictures become really, really essential. So if I come back into a series circuit now and I want to find I1 and V1 and I23 and V23, so remember this R23 we said is 12 ohms. So since I'm unpacking this or uncollapsing this into a series circuit, what is constant? My current or my voltage? So I'll give you a hint here again, SCC, PVC. In a series circuit, our current is constant, series current constant, which means this current has to be the same across both of these resistors. So I1's current is going to be 0.545 and I23's is going to be 0.545. So I can literally look at this like this. This is going to be 0.545 and then this is going to be 0.5, hard to draw sideways here, 545. So this guy is the one that's backwards, 545. Okay, and that'll be amps, and that'll be amps. So now, that's a brain challenge, right sideways. So now, can't I do Ohm's law for each of those voltages and multiply my current and my resistance, multiply my current and my resistance? And when I do that for V1, 10 times 0.545 is going to be 5.45. So this would be 5.45. And then for V1, 2 together, 12 times 0.545 is going to give me 6.545. So this will be 6.545 volts for V23 together. Now notice that didn't we just finish resistor 1? So we are all done with resistor 1. We don't have to worry about it anymore. Working backwards, though, we still want to know what 2 and 3 are. So we're going to have to uncollapse R23 back into I3, V3, and I2, V2. And think through in a parallel circuit, because these are parallel, what is constant in a parallel circuit? The voltage or the current. And again, back to SCC, PVC, parallel voltage constant. So this 6.545 has to be the same for both of these. 6.545 is V3, 6.545 for V2. So this is both going to be 6.545 and 6.545. Now, again, can't we do Ohm's law to find our currents in each of those? So I'm going to take and multiply or take and divide 6.545 by 30, and that gives me 0.218. So that's going to be I3, 0.218. And if I take 6.545 and divide by 20, that's going to give me 0.327. 0.327. Now think through, can't we double check? In a parallel circuit, don't our currents add up to give us our total? So if I take 0.2 plus 0.3, don't I get 0.5? Now this isn't going to be quite exact, although in this case it looks like it is, but it may be off just slightly because of rounding. But in general, you'll notice that those two add up to give us our total current. And that's how we would do a complex circuit. Okay, so here we go. Final complex circuit. We're adding a little bit more to the one we just did. So see if you can do this one step ahead of me. I already filled in the values. We're going to go with the same things we had earlier for R1, 2, and 3, 10, 20, 30, and we're going to add an R4 that's going to be 40, but we'll keep our total voltage as 12. Now I put my labels up at the top just to make my numbers a little easier. This column is all volts, this column is all amps, this column is all ohms. So remember, the first thing that we want to do is we want to collapse our circuit. So we want to look on this circuit. Is there an easy place that we have either two resistors that are in series or two resistors that are in parallel to collapse? And your answer to that should be, that's right, R2 and R3. Notice that R2 and R3 are in a very basic series circuit here. So I'm going to collapse my resistors. I'm going to draw a new one here. I'll have my R4 coming down here then, I'm going to have R2 and 3 together, R2, 3. And then come over here where I'm going to have my R1 will be over on that one. And when I look at that, now think through how do we combine resistors that are in series with each other? And the answer to that is they literally just add up. So I'm going to take my 20 plus my 30, and I'm going to get an R23 value of 50 ohms for that guy. Okay, next up, whenever I look at this, what's the next thing that I would collapse? And your answer should be R1 and R2, 3, because aren't both of those in parallel with each other? So now I can put those together. So I'm going to have my R4 up here, and then I'm going to combine these over here into an R1, 2, and 3. Now remember to add up in parallel. We can't just add them because it's an inverse relationship. The more resistors we get in parallel, the lower the resistance is. And so we have to do the 1 over plus 1 over plus 1 over. So I'm going to have 1 over 50 plus 1 over R1, which we said was 10 ohms. So 1 over 10. And then I'm going to flip it one more time. And whenever I do that, I get an R123 value of 8.33. So 8.33 ohms is my 1233 value. Is my 123 value. Then if I look at this, I have one more thing that I can collapse. I still have my R4 up here, which is just hanging out. It was a 40 ohms, but now isn't that one in series with 1, 2, and 3? So I can put those together to get my final value, which will be my total resistance, RT, or R1, 2, 3, 4. And in a series circuit, what do we do to put those together? Yes, again, we literally just add those up. So I'm going to take 40 plus 8.33 and get a value of, I don't know, maybe I should pull out my calculator, 48.33. And that's going to be my ohms for that, for the total resistance. So now I can fill in this total resistance here of 48.33 ohms. And look at the beauty of that. If I know my total voltage here is going to be 12 volts, then can't I find my total current by dividing the two of those using Ohm's law, V equals IR. So when I divide the two of those, I'm going to get a total current of 0.248, 0.248 amps, and that's going to be my total current running down or through the circuit. Now, remember that these pictures are really, really important. A lot of students, they can get here mentally where they can collapse the resistors, but the problem is they have trouble going backwards mentally. And so your pictures help guide you going backwards to find the individual values, because now we want to go back and find what is the current and voltage across each of the individual resistors. But to do that, we have to uncollapse our circuit back in that series, parallel, series, parallel, series, parallel. So if I'm unpacking or uncollapsing this total backwards into this guy, then aren't I going to have an I123 and a V123? And then I'll also have an I4 and a V4. And to calculate those, if I'm coming back into a series circuit, what is constant, the current or the voltage? And I hope that by now you can resoundingly say SCCPVC, series current constant, parallel voltage constant. SCCPVC, series current constant, parallel voltage constant. So in a series circuit, our current is constant, which means that these two resistors will have the same current as what it was when they were together. So this would be 0.248. This one would also be 0.248. And now can't we use Ohm's law to calculate the resistors? So I'm going to take 40 times 0.248, and I'm going to get a voltage of 2.069. And I feel like something is not right about that. So if I take, oh, I'm sorry, I did the wrong one. That's actually this one over here. So 8.33 times 2.248 is going to be 2.069. And if I take this guy, I'm going to take 40 times 0.248, and that's going to give me 9.931 volts. Okay, now again, remember that in a series circuit, shouldn't our voltages add up to give us our total voltage? So if I take 9.9 plus 2.0, doesn't that give me roughly the 12 volts that I have for my voltage there? Now, aren't we done with the R4 so we can fill our table in here? So this is going to be 9.931 is going to be my 4 voltage, and my I4 is going to be 0.248, and that finishes out that guy. Now, moving backwards, can't we unpack or uncollapse 1, 2, 3 into 2, 3, and 1? So I'm going to say there's an I1 and a V1, and there's an I23 and a V23. And in a parallel circuit, what is constant? My current or my voltage? And I hope you would say by now, it's my voltage. So this is going to be 2.069. This will be 2.069. And can't we use Ohm's law to calculate what the currents are? So I1 is going to be 0.2069, and I23 is going to be 0.04138. And again, we can double check this. If I add those two currents together, do I roughly get 0.248? And the answer to that is yes. So aren't we done with resistor 1 now? So I can fill in that V1 is going to be 2.069, and I1 is going to be 0.2069, and that gives me 1. Now we have only one more to go. We have 2, 3 that needs to be split back into 2 and 3. So I'm going to flip back into, maybe we'll use gray here. So I3, V3, I2, V2. And in a series circuit, what is constant? Our current is constant, so this 0.04138 has to be the same. 0.04138 and 0.04138 has to be the value for those currents. And we can use Ohm's law now to calculate what the voltages are. And V2, if I take 20 times that 0.04138, I'm going to get 0.8276. 276. And if I take 30 times 0.04138, I'm going to get 1.241. And again, if we add those two voltages up, then we should roughly get this 2.069. And looking at those numbers, it looks like that's exactly what we're going to get. So now, aren't we done with 2? And we can fill 2 in. This will be not 20. The voltage will be 0.08276. And the current will be zero. Sorry, I had a brain fart there. I thought maybe I had miscalculated that. Will be 0.0, or written it wrong. Wrote it wrong. Words today, they just are failing me. So 0.04138 is going to be the current. And then remember that current was the same for I3, 0.04138. And the voltage we came out to be 1.241. Okay, all of that to say, we just found what the individual voltages and the individual currents are on each one of those resistors. And remember, what makes this a complex circuit is that it's not just a basic series or basic parallel. We have a combination of series and parallel resistors, or series and parallel light bulbs, that are all put together, and we have to collapse them one at a time in series or parallel, and then flip-flop to the other one all the way down until we get over here to our total resistance. And then we have to uncollapse those backwards to find out what the individual currents and voltages are for each of those. So I hope this series of videos helps, where you have a simple series, a simple parallel, then you have a simple complex circuit, like simple, not simple circuit, but it's like an easier complex circuit, and then you have a more complex circuit for that. And I hope that helps you as you are going through and solving some of these problems.